Hello Calc 3 and welcome back to another video. So in this video we'll cover section 15.7, just the first half where we talk about triple integrals in cylindrical coordinates. So remember from section 15.4 that we defined a double integral for functions in polar coordinates or regions in the plane in polar coordinates. And in this section, we're going to define triple integrals for a generalization of polar coordinates to three-dimensional space. And in particular, that generalization will be called cylindrical coordinates. And there will be another generalization in the second half of section 15.7 called spherical coordinates. But for today, we're just going to worry about the cylindrical coordinates. Okay, so before we can talk about integration for cylindrical coordinates, we first need to describe what cylindrical coordinates actually are. So cylindrical coordinates represent a point P in three-dimensional space by ordered triples, which are typically denoted r, theta, z, in which r is always greater than or equal to 0, and r and theta are polar coordinates for the projection of the point P down onto the xy plane, and z is the rectangular vertical coordinate. So there are a couple of different ways to think about this intuitively or practically. The first way, maybe you want to think of yourself standing at the origin and you turn theta degrees from the x-axis until you're facing the point P in space, like you can see in the diagram here to the left. After you turn and you're facing the point, then you can walk out r units in that direction until you're directly underneath your point, and that'll give you your coordinate r. And then finally, you can go directly up or down z units, depending on whatever your coordinate z is, until you actually reach the point. So that's one way to think about it. You could also think about it as saying, okay, well, the z coordinate is going to determine the plane perpendicular to the z-axis on which my point lies, and then r and theta just give polar coordinates for that point inside of that specific plane that's perpendicular to the z-axis. So either one of those intuitive ways to think about cylindrical coordinates would be fine. You can just choose whichever one makes most sense to you. We also have equations that relate between rectangular coordinates and cylindrical coordinates. And all of these equations are just pulled over from equations we had relating rectangular coordinates and polar coordinates, except for this particular equation here, which just says that z is equal to z, and that's just because z is going to be a rectangular coordinate in both cases. So in cylindrical coordinates, z is still just a rectangular coordinate. But we do have x is equal to r times cosine theta, y is equal to r times sine theta. We still have r squared is equal to x squared plus y squared, and we still have tangent theta is equal to y divided by x. Okay, so here are just a couple examples of some common surfaces given in cylindrical coordinates. So if we have the equation r is equal to a in cylindrical coordinates, that means that r is going to be constant, and that'll give us a cylinder around the z-axis of radius a. So notice here that we don't have any restriction on theta, so theta is free, which is why we have, if we kind of drew a circle, if we drew a circle in the xy plane, we're going to have the whole circle contained here for this equation r equals a, because theta is not restricted at all, and then z is not restricted at all either. And so we have a cylinder that goes all the way up and down the z-axis, kind of like this. And yes, I know that this drawing is kind of bad, but hopefully you at least get an idea of what that would represent. If we have r equals 0, so this is just a specific case of the more general case r equals a, then we're only going to get the z-axis, because in that you can kind of think about it with the picture that I just drew. You're taking the circle, and because the radius is equal to 0, you're just pulling it all the way into the z-axis. And so all you're left with is the z-axis. If we have the equation theta is equal to some particular theta naught, then that's going to give a plane that goes through the z-axis. So here I have a ray with angle theta naught from the x-axis in this case. Yeah, so I'm going to call this the x-axis. This is going to be the y-axis. And so we have that ray that makes an angle theta naught with the x-axis. Then theta equals theta naught is going to be that vertical plane that that's parallel with theta naught and intersects the z-axis, or contains all of the z-axis. Okay, so cylindrical coordinates are particularly nice for describing cylinders inside of space whose axes run along the z-axis or just parallel with the z-axis. In the example that I gave above, the cylinder actually had the center, or the central axis of the cylinder was the z-axis, but you can also have cylinders that are simply parallel to the z-axis that have different central axes. And also planes that contain the z-axis, so that would be like the case theta equals theta naught, or lie perpendicular to the z-axis. So that would be when you just have some constant z, like z is equal to 2, then that'll give you the plane that's perpendicular to the z-axis and intersects the point 0, 0, 2. So those are just a couple different examples of regions inside of space that are nice to describe using cylindrical coordinates. And now we can develop the triple integral for cylindrical coordinates since we have an understanding of what these things are. So the process is going to be very similar to almost all the other sections in this chapter. So we subdivide some region in space into cylindrical wedges in this case. So remember from the definition of the double integral for polar coordinates, we subdivided our regions into what we called polar rectangles. Well, these cylindrical wedges are going to be similar to the polar rectangles in that if you look just at the base of this cylindrical wedge, which I will try to outline here, so this base right here, that's just going to be a polar rectangle, but we add the z dimension right here, and now we call that a cylindrical wedge. So it's a polar rectangle that has a third dimension in the z direction. And the volume of each of the wedges is going to be given by the area of the polar rectangle that's consisting of, or that's creating the base of our cylindrical wedge, multiplied by the height of the wedge, which just ends up being r times delta theta times delta z. And so the Riemann sums are going to look like S sub n is equal to the sum from k equals 1 to n of f of r sub k, theta sub k, z sub k, times r times delta theta times delta z. And that's a lot of things to say, but what that means at the end of the day is that the triple integral of f of r theta z, so some function in cylindrical coordinates, over the region D in three-dimensional space is equal to the limit of those Riemann sums, so the limit as n goes to infinity of s sub n, which is equal to the integral of f of r theta z dz r dr d theta all over the region D. And from there we can define the triple integral to be repeated integrals or integrated or iterated integrals. Okay, so let's move into our first example then. We want to find limits of integration in cylindrical coordinates for integrating some function f of r theta z over a region D, and that region D is bounded below by the plane z equals 0, or just the xy plane. It's bounded laterally, or from side to side, by the circular cylinder x squared plus y minus 1 squared is equal to 1, and it's bounded above by the paraboloid z equals x squared plus y squared. Okay, so the process for the solution is going to be the same as it's been for the rest of the chapter. So we're going to sketch our region inside of three-dimensional space here. To do so, we can sketch the paraboloid, which is the graph that I have in purple. And we can also sketch that circular cylinder x squared plus y minus 1 squared is equal to 1, which is the graph that I have in red. And both of these things we can sketch by hand. We don't need a computer for this. So when I look at the circular cylinder x squared plus y minus 1 squared is equal to 1, well, x squared plus y minus 1 squared is equal to 1. If I'm only thinking about the xy plane, is going to give me a circle that's centered around the point 0, 1. And so if I add the fact that z is unrestricted, that's just going to give me a cylinder that kind of goes up out of the xy plane around the circle that's centered at the point 0, 1 of radius 1, which is exactly what I've drawn in red. And then after we draw the paraboloid, z equals x squared plus y squared, then we have an idea of the region that's going to be bounded by those two things. So that region is the region that I have drawn in blue there. If you want a better picture of what that looks like, you could also open up your book and look. I think that your book has a pretty nice picture that might be it might show a little more explicitly exactly what region we're talking about, but this is as good as I could do. Okay, so we can define or describe all of the functions that are given to us in cylindrical coordinates as opposed to rectangular coordinates. So z equals 0, which is the bottom bound for our region, that's already given in cylindrical coordinates. But we also have z equals x squared plus y squared, but x squared plus y squared is equal to r squared. So in cylindrical coordinates, that gives us z equals r squared. So we have z equals 0, we have z equals r squared, and then finally we have to convert this x squared plus y minus 1 squared is equal to 1 to cylindrical coordinates. So we can expand the y minus 1 squared and get down to x squared plus y squared minus 2y is equal to 0, but x squared plus y squared is equal to r squared, and so we have r squared minus 2y is equal to 0, and then we can substitute r times sine theta for y, and do a little bit more algebra, and our final equation is going to be r equals 2 sine theta. So now we've taken each of the functions that were given to us that describe our region, and we've given them in terms of cylindrical coordinates. And once we're at that point, now we can focus on bounds or the limits of integration for the variables z, r, and theta. So theta is going to be bounded by 0 and pi. So if you look up at our diagram here, theta, the lower bound for theta is going to be along the x-axis, and the upper bound is going to be along the negative x-axis, so up here. And along the x-axis we have theta equals 0, along the negative x-axis we have theta is equal to pi, so that's why we have thetas between 0 and pi. We also have that r is between 0 and 2 sine theta. So if you start at the origin and you draw lines out through the circle inside of the xy plane, you'll see that r is always going to enter that circular region at the origin 0, and it's going to exit at the curve describing that circle, which is 2 sine theta. And lastly, we have our limits of integration for z. So if you pick a line inside of the circle in the xy plane, that gives the projection of our region onto the xy plane, and you go directly up through the region, you'll see that z enters the region at 0, and it's going to leave the region at the function giving us the paraboloid. So z is going to be bounded below by 0 and bounded above by r squared. And so we can finally write the triple integral as the iterated integral, where we have the integral from 0 to pi, of the integral from 0 to 2 sine theta, of the integral from 0 to r squared, of f of r theta z, dz, r dr, d theta. Okay, so I expect that many of you, after just seeing that first example of finding the limits of integration, would be comfortable with finding the iterated integrals that represent the triple integral in cylindrical coordinates. But I do want to go through the more general process here for all kinds of questions that we get where we have to integrate in cylindrical coordinates. So to evaluate the triple integral of f of r theta z over the region D, where we are integrating with respect to z and then r and then theta, there are going to be 4 different steps that are very similar to the 4 steps we had in section 15.5 for rectangular coordinates. So the first step is to take our region D in 3-dimensional space and just sketch it along with its projection onto the xy plane. So if you look in the diagram here, we have the region D that's sketched up in space somewhere, and then we also have the region R down in the XY plane that represents the projection of that space down onto the plane. So after we have our working sketch, so we know what things look like, then the next step would be to find the limits of integration for the variable z. So to do that, we can draw lines that are perpendicular to the region R that go up through the region D in space. So just pick some point inside of R and then draw a line that goes straight up, and it should go up through the region D. And we want to make note of when the line enters that region and when the line leaves that region. And so in the diagram that we have here, we have that lower surface is defined as z is equal to g sub 1 of r theta. So that would be the function giving the lower limit for z. And then we have the upper surface is z is equal to g sub 2 of r theta. So that would be the upper limit for the variable z. After we find the limits of integration for z, we can move on to finding the limits of integration for the variable r. And to do that, we're going to draw lines that start at the origin in the xy plane that go through the region R in the plane. And again, we're going to note when the line enters and leaves that region R. So in this case, you can look down at the diagram. We have the line L given to us. It starts at the origin and then it goes out through the region R. And the line enters the region at r is equal to h sub 1 of theta in this case, and it exits the region at r is equal to h sub 2 of theta. So in this case, the lower limit for r would be h sub 1 of theta, the upper limit would be h sub 2 of theta, and then we can finally use the same diagram that we have above to find the theta limits of integration. And at this point, the limits of integration for theta, the last thing we integrate with respect to, should be constants. So in the image above, theta is going to be bounded below by alpha, and the upper limit of integration is going to be beta. So again, you can start at the origin and draw rays out from the origin that have to completely contain the region R, and that'll give you your lower limit for theta, in this case alpha, and your upper limit for theta, in this case beta. Okay, so then using the functions that were defined in the diagrams above, we have that the triple integral of f of r theta z over the region D is equal to the integral from alpha to beta of the integral from h1 of theta to h2 of theta of the integral from g1 of r theta to g2 of r theta of f of r theta z dz r dr d theta. And again, do recognize the fact that we have this extra r that's put in there because we're integrating. After we integrate with respect to z, then this problem really becomes about integrating a two-dimensional region with respect to polar coordinates, which is why we would have this extra r that pops in. And finally, we have the last example for the video here. So it is a relatively short video. So let's say we want to find the volume of the solid enclosed by the cylinder x squared plus y squared is equal to 4 and bounded above by the paraboloid z equals x squared plus y squared and below by the xy plane. Okay, so I spent a little bit of time here trying to draw this region in space in a way that was easy to see, and it was difficult for me to do. So I decided to use the drawing that the book gave, but that's not because the sketch can't be given by hand. Both of the surfaces that are given here, this x squared plus y squared equals 4 and z equals x squared plus y squared, are surfaces that we should know offhand, and you can sketch them. It was just difficult for me to show that we're talking about this whole green region that surrounds the paraboloid in the center. It was difficult for me to represent that pictorially, so I just used the book's picture. If you look at the example that the book has, they actually talk about calculating the centroid for this region that we're talking about, but that's a topic from section 15.6, and we're not going to be covering section 15.6. So I just adapted the examples that we're finding the volume of this region. So the first thing we want to do is take the functions that are given to us in rectangular coordinates and convert them to functions in cylindrical coordinates. So first we have z equals x squared plus y squared, and that's just going to go to z equals r squared because x squared plus y squared is equal to r squared. We also have x squared plus y squared is equal to 4, and again that's just going to go to r squared is equal to 4 because x squared plus y squared is equal to r squared. And lastly, we have that it's bounded below by the xy plane, which would just be the equation z equals 0, which is already in cylindrical coordinates, so we don't have to worry about that. Okay, and from here, we want to find the limits of integration for the variable z. So if you pick any point inside of that region R down in the xy plane, and you draw a line that's parallel to the z-axis going up through our region, then that line is going to enter when z equals 0, or at just the xy plane, and it's going to leave when z equals r squared. So it's going to leave at the paraboloid in blue. So that'll give us the limits of integration for z. Then we can worry about limits of integration for r. So again, if you start at the origin and you draw a line from the origin out through the region R, or any point in the region R, then that line is going to enter the region R at 0, and it's going to leave the region R when R is equal to 2, or just that circle that's describing the region R here. So R is equal to 2. And that'll give us the lower and upper limits of integration for R. And then finally, we need to worry about lower and upper limits of integration for theta. But theta is going to go from 0 to 2 pi because we're talking about this whole circle here in the xy plane, not just part of the circle. So the lower limit of integration will be 0, and the upper limit of integration will be 2 pi. And so then the volume will be equal to the triple integral of dv over the region D, which is equal to the integral from 0 to 2 pi of the integral from 0 to 2 of the integral from 0 to r squared of dz times r dr d theta. And so first we take the inner integral, so we take the integral of dz, which gives us z evaluated from 0 to r squared. If we do a little bit of simplifying again, we get the integral from 0 to 2 pi of the integral from 0 to 2 of r cubed dr d theta now. And then we want to take the integral with respect to r, so we get 1/4 times r to the 4th evaluated from 0 to 2. And we can plug in a 2 and get 4. So we're left with just the integral from 0 to 2 pi of 4 d theta, which is equal to 4 theta evaluated from 0 to 2 pi, and we plug in 2 pi for theta and get 8 pi. So the volume of that region that kind of looks like a bowl surrounding the paraboloid z equals x squared plus y squared is going to be equal to 8 pi. Okay, so that's the last piece of information for this video. The next video that I put up will be the second half of section 15.7, where we will talk about spherical coordinates as opposed to cylindrical coordinates and evaluating triple integrals in spherical coordinates. So you can look forward to that.